Morning, everyone. So my presentation is mostly containing data from the last year's Tau Herculids, and in the end, I will talk a bit about this year's Perseids. Just from last year, if you don't remember my talk, a small expedition of four went to Texas to record data from the Tau Herculids. They used the Sony Alpha 7S camera. It is very widely available, and the main motivation was to see if we can record the meteors and do any observations or data reduction using off-the-shelf equipment. Basically, we recorded over 800 meteors, of which around 650 was Tau Herculids, and now let's see the results. We have many meteors. Some of them are faint, some of them are bright like this. You can hear the excitement of our fellow observers. Yeah, so some were bright, most of them were really faint, like 7 or 8 magnitude. A lot of the data was populated by meteors like this. And afterwards, we carefully curated them, which means that we watched through the recordings. And just like in the good old days, when someone saw a meteor, shouted top, and then stopped the video and recorded when it happened. Afterwards, we named each meteors if we wanted to have an analysis case by case. We estimated brightness, also the old way, and calculated the path and other shower statistics. So the naming convention, with the normal UTC, we also added polar coordinates, which is regarded to the position within the frame. This is necessary because sometimes we had like 2 or 3 meteors at the same time. So in this video, you can actually see 3 meteors. 2 of them are fairly visible and easy. The third one, I won't say where it is. Let it be an Easter egg hunt for you. So we named each of them. This was tedious. So we had 3.5 hours of data, and this took like 1.5 weeks to do so. So it's a long process. And afterward, we doubled down and said, let's put more time into it. Using the brightness estimation, we used the most developed technology made by evolution ever, the human eye. So we watched the meteors again, and using comparison stars that you can see here, we estimated. The pro thing is that it's a quick thing. So you look at the meteor and you see it, estimate it, it's done. It's also easy. The con, it is actually not quick. So you have to watch through every single recording. And sometimes we didn't have enough comparison stars, so it might contain systematical errors. For example, with brighter meteors where there are no such stars in this visible range. You can see our graph here with our estimates. It's a bit rough. I can say it, and using that, we calculated the population index of the shower. You can see some other values from the last year, and the good thing is that R is the biggest, so that's a win. And it's positive. This is also great, but of course it needs to be refined a bit more. Probably the estimation was not correct. We used the path later to calculate the radiance. First, we used 2 methods. One we nicknamed the moving cluster method, because it uses the same principles that astronomers use with moving clusters to determine the star's origin null place. So you can see it here. It's really nice, not that useful. The other method was pairing random pairs of meteors and then calculating the radiant with sigma clipping. It was nice, but we could only use it with random pairing. then I tried to pair every single meteors with every other thing meteors. We ran into a problem there. So when I pressed enter, yeah, it said 7.8 days, and just in 1 hour, it risen to 8.5 days. So that was not that useful. The mistakes that we made with this method were many. I coded in Python, which is a slow language. I also messed up the math several times. Then I used ChatGPT to make it a bit faster. It didn't help that much. Maybe the biggest problem was trying to calculate nearly 4,000 pairs of meteors, and many other mistakes, which I have no idea, because we moved on to a new approach. This contains calculating the great circles of each and every meteors and then plotting them on a heat map, and just guessing that maybe the density of these circles will show the anti-radiant and the radiant of the meteor shower. Over there, it is useful because it scales with the number of meteors linearly, and it is also useful because in radio astronomy, we have a lot of tools to analyze these kinds of plots. So that was our guess that we can maybe steal some methods from other areas of astronomy. With this, we calculated the radiant, which is somewhere there where others say it is supposed to be. We can see a long shape there. This might be systematical error, but also we did not separate meteors by time. So we heard yesterday that the radiant was shifting during the night and also during the previous night. So it might be because of the shifting radiant. It also might be some systematical effect there. To further improve this technique, we need to have a wider angle lens because yeah, it helps if you see more part of the sky. It is also useful if we have multiple cameras because you can see yes, the shape, but also we have these two branches coming out of the radiant. So during the night of 21st of May last year, the team recorded meteors from two positions from the sky. So these lines are due to one of these positions and this for the other. So we guessed that if we had many more Sony Alpha 7 cameras pointing to the different directions, then also these parts of the sky could be populated. That might eliminate the shape of the radiant, and it might also give more precise data for this. Yes, as I said, it's great because it scales really well with a large amount of meteors. And using this method, we also tried analyzing Perseids. Well, trying means that we have recordings, and this is where we finished with the thing. We didn't have time. So far, we have 18.5 hours of recordings of meteors such like this. Once again, the excitement. So lots of these, we spent 4 nights at Piszkéstető in Mátra, Hungary. We recorded God knows how many meteors. I saw more than 700 during those days. On the 13th, it was more than 400. The problems that we have 18.5 hours, which we estimated would take like 2.5 weeks if we didn't do anything else than just watching the videos. So automation is much needed for this. But it's also a lucky thing that I'm writing my thesis of this, so I won't have time for anything else, and I can do it probably. But more help is needed. If anyone wants to watch videos of Perseids, then please call us. Thank you.